Hello everyone, welcome to Set Partners track of the Set Experience Academy webinar series. I'm Luis Fausto, I'm a technology and regulatory specialist with Global, and I'm here with Ralf Schaefer. He's VP Standards, Research and Innovation at Interdigital, and he's here with us to share his presentation on thoughts on TV 3.0 video formats. Ralf, over to you.
Thank you very much, Luis. I'm very happy to be here tonight. So I will start my presentation. So here we go. So this is a common presentation of Technicolor Philips and Interdigital. The title is Thoughts on TV 3.0 Video Formats. So TV 3.0 is a next generation hybrid TV system where backwards compatibility to 2.0 or 2.5 TVs is not a requirement. It comprises a broadcast file, broadband, transport, the audio and video codecs, captions, and also interactive applications. So requirements for the video component ask for top-notch features. So we look for up to 8K resolution, up to 120 frames frame rate, wide color gamut, and also 10-bit coding, high dynamic range, and also new video features for VR that go up to 6 degrees of freedom. To be complete, the video component also includes a display manager for multiple videos and also an emergency warning manager, but these two, we don't cover them in the presentation here. So with the following slides, we would like to present you the new video coding technologies in reach for TV 3.0. So there's a second episode that will deal with the comparison of video codec solutions. This comes in a separate episode, and in this episode here, I cover the high dynamic range and TV 3.0, an introduction to the MPEG-I virtual reality formats, and make a conclusion. So this is the other episode, and we start here off with high dynamic range. So high dynamic range becomes mainstream in TV 3.0. So I copied here some of the requirements, and we see that HDR is required over the air and also over the internet. SDR is no more required over the air delivery, but it is still required over the internet. And HDR dynamic metadata is desirable over the air and required over internet delivery. So HDR10 based HDR solutions are the most future-proof. So this is our opinion, because the peak luminance goes up to 10,000 nits, and this is really sufficient for many years in advance. But dynamic metadata-based solutions solve the HDR10 display mapping issue. So this is when consumer TVs have different issues when displaying static HDR10 content, not optimized for the peak luminance. So you can have clippings or loss of details or crushed blacks. And here, dynamic metadata help to solve these issues. But we see also that SDR backwards compatible HDR solutions are still of interest, because over OTT delivery, we have non-TV devices, and there may still be SDR for a long time. And also backwards HDR solutions that support SDR and HDR in the same bit stream, save bandwidth over the networks, and also storage space on servers. So let's have a quick look in Technicolor HDR. So we have here on the left side a quick view on static HDR, which is just HLG and HDR10 with static metadata. Here the metadata is constant and identifies the EOTF and capabilities of the reference monitor. But with dynamic HDR solutions, you have a dynamic process that optimizes each image from any reference HDR down to SDR or any intermediate HDR thanks to dynamic metadata. And also the dynamic metadata enables display mapping. From Technicolor side, we have 3 different solutions. They're all specified in TS 103433. It's a multi-part document that has these 3 subparts. So there's SLHDR1, which is an SDR base layer plus dynamic metadata. It allows high quality SDR and HDR without a simulcast. It's standardized in ATSC 3.0 together with SHVC, and also standardized already in SBTVD for TV 2.5. We have SL-HDR2, which is HDR10 based plus dynamic metadata. It's backwards compatible with HDR10, and it's standardized in DVB and Candida is standard in China. And SL-HDR3, this is the newest in the family. It's HLG based plus dynamic metadata, and it corrects HLG limitations and enables high quality images on all displays for SDR and for HDR. In our solution, everything is fully standardized. So it contains, on the one hand, the metadata specification itself, but also the reconstruction process. So it's possible, really, if you take different TV sets from different brands, that they can use the same reconstruction process. And so from the content provider side, you know better what is the result on consumer TVs. So now we look into VR formats, because these are also requirements in TV 3.0. And we look into what MPEG has prepared. So on the left side, we see the point cloud activity. So this allows to go up to 6 degrees of freedom. So a point cloud is in fact a set of points in 3D space where the points have no direct relation. And the point is, it's on the one hand geometry, so it means the coordinates, and it has also attributes. So attribute can be color, transparency, or temperature, and so on, depending on the need. So this is on the left side. On the right side, we see another format that MPEG is preparing. It's called MPEG Immersive Video, so MIV. So this is more adapted to 3 degrees of freedom plus. So and this is typically recorded by a camera rig, as we see on the right side. And this generates all these nice videos. And it's a very efficient way how to transmit these different views to an end consumer device, so as to have this 3D plus view where you can move a little bit in front of the screen and get different views of the scene. So both approaches are complementary, they're a bit different. So the point cloud approach allows really 6 stuff. That means you can, for example, from this horse here, you can really walk around and watch it from all sides, but you don't get a complete scene directly. And here with the MIF approach, you get a complete scene directly, but you cannot freely move around. So they're complementary. So the next slide shows here a little video. So we show here an implementation of so-called VPCC on a mobile phone. So this is implemented by InterDigital on the phone, and the content is coming from 8i. So I'll launch now that video. And you see this, this background is coming from the camera, from the mobile phone. And this lady is a point cloud that is stored in a compressed manner on the phone. And it's decompressed in real time and played back. And you see when you go closer to the lady, she becomes taller. You can completely move around her as she would really be in the room. So this is an interesting approach, a demo for 6 stuff. So on the right side here, we see a content from Intel. So this is for sports, for example, an interesting scene. You can just freeze it at a moment and then watch it from any angle that you would like to see. And this is also implemented as a point cloud. So the basket is a point cloud, and the scene around is 360 videos. It's a composition out of it. So this shows a little bit how this can be used. Now we move on. We look very quickly, in fact, how this is working out. So the point cloud gets into this encoder, and then this is projected to the six planes of a cube. You get these different pieces. You get this for texture. You get this for depth. You put this on a sort of common canvas. So from all 6 sides of the cube, you put it on the same canvas, and you get then a geometry image where all the pieces are in. You get a texture image. You get an occupancy map, and all these become videos that you see like that. So you do at the end 3 different video encodes at the same time, one for texture, one for depth, and one for the occupancy map. And you have some metadata that describe how to reposition these different patches in 3D space. And all this is multiplexed and put into a bit stream and sent out. And the interesting thing is, with this approach, you reuse existing video codecs. So MPEG used first HEVC but also first tests with VVC have been done. And with VVC, we gained already 30%. With HEVC, we reached compression ratios up to 300:1. That means this point cloud lady can be transmitted with around 6 to 8 megabits of data, and which is quite efficient. And with VVC, it can even be done better. So let's have a quick look at the MIF case. So this is on the one hand for light field displays that are all for HMDs. So HMDs often nausea appears after viewing a longer time, and MIF introduces parallax, and so it's much more comfortable to view content with HMDs. And here I show a demo. Went too far. Need to launch the video. This is becoming full screen. So what we do here is the colleague gets a sensor, and that the screen can detect where he is. And now we see here, when he moves in front of the screen, the scene is changing and it's adapted to his view. And it's exactly what has been captured before with this multi-view rig. It can be reproduced, and MIF transmits this in a very clever manner. And we see that on the coming slide, how this is done. So you have this MIF information, so multi-view per steps that goes in. You produce out of that you do a sort of pruning. You remove all the redundancies first, then you create patches by some clustering, and you see then that you get a main scene, and all these small patches here are pieces that describe occlusions or views from different directions. So all this is then compressed. So this texture image, this depth image, we see this here. It comes everything together. We have again 2 video encodes and also some metadata, and this is sent out over the network. And we remember well what I have shown some minutes ago about point cloud. We have similar things. We have a texture image, we have a depth image, we have some metadata. It's a similar bit stream that can be used, but it shows 2 complete different applications. So the conclusion with all that, so VVC has been finalized 1st of July 2020. So this makes a little bit reference to the other episode that my colleague Michelle will show very soon. And VVC, okay, it has significant increase in subjective and objective compression performance. And also the team made a very good balance between compression performance and computational complexity. For example, the decoder is about 2 times more complex than HEVC. So for dynamic metadata, what is here in my presentation, you can say that HDR-based solutions become really the mainstream with TV 3.0, and that as an HDR, which is a dynamic metadata-based solution, it covers all transfer functions, so HLG, PQ, and also SDR. So depending on what TV 3.0 will choose, everything is in there and can be used. And we have also seen that MPEG has prepared 2 powerful complementary VR formats that can run very quickly on consumer devices. So MPEG VPCC has been finalized July 1st, 2020, the same time as VVC. And the MIF specification is a little bit later, but it's still compatible with the TV 3.0 work plan in case that SBTV is interested. So both formats share the same bitstream and syntax and semantics. And all this is available from MPEG. Yeah, thank you very much. It was a pleasure to give an update on these technologies. Thank you.
Thank you very much, Ralf. I had 2 questions for you. The first one, is SLHDR compatible with new video codecs such as VVC that you mentioned?
Yeah, this is an interesting question. Indeed, SLHDR is principally compatible with all video codecs. So far it is specified for AVC and also for HEVC, and it is using SEI messages. So basically what needs to be done is really to specify the SEI message for the new codec. So this is not a lot of work to do, but of course it needs to be standardized. And for this we have launched 2 weeks ago 3 work items in Etsy to update as an HDR1, 2, and 3. So there will be a new annex with the SEI messages for VVC. So this will be ready in time for TV 3.0.
Thank you, Ralf. The last question, you mentioned some new VR formats. For which end user devices these new formats are suitable?
Yeah, so we have seen in the presentation that first implementations on commercially available mobile phones is already possible. So this is implemented as an app, and I have shown that this is based on existing video codecs. So a mobile phone today, for example, can run multiple decoders at the same time. So this demonstration, for example, can run over 3 hours on such a mobile phone just by decoding the point cloud all the time. So even battery life is not a big issue. So mobile phones is an interesting device, but also TV sets. It's possible in future to get such formats to TV sets. And even without new hardware support, it's probably also possible to run it quickly on TV sets.
Thank you, Ralf. Thank you very much for sharing this presentation with us. I hope we see you other times in future set webinars. Bye-bye.
Yeah, it was a pleasure. Bye-bye.